Welcome to the sixth and final session of the Amateur Radio Technician Licensing class. Today we're going to start with, or focus on electrical safety. And I'm going to start with David's rules of safety. And they're kind of tongue-in-cheek, but you'll get there is an important point here. As you can see, the first is the law of cognitive perception. You may think you're an 18-year-old, but your body may be a lot older, out of shape, and more fragile. Ask for help. And even if you are 18, ask for help. The next is the law of situational discernment. Before starting, take a breath, clearly see the situation and potential hazards, size things up, understand your limits, think it through, give it another thought, and then act. The third law is the law of negative dexterity. Anything that can slip out of your hand will do so in a way and at a time that directly or indirectly will damage the item and or some other critical piece, cause an injury to you or someone else, and or be lost and end operations. Assume droppage and prepare accordingly. The law of reaching the ground state. What goes up, including you, has the potential to come down in an uncontrolled fashion. Take precautions to prevent the ground from suddenly rushing up to you. Now, Law 5, the law of urgent warning. If a little voice in your head, an associate or spouse says, "Don't do this, it's going to hurt," should we take a step back and think about this some more, or do you think safety equipment is needed? Stop immediately and see Rule 2, assess, then validate or cancel the potential action. The law of confirmation. When working on a circuit or machinery, assume it's energized or pressurized until such time as you've confirmed the fact yourself. 7. The law of attraction. When one sees a button, switch, knob, object, or slider, he or she will be tempted to interact with it, to touch, move, or press it, even if it's big, red, and has lots of warning labels on and around it. Fight this urge, step away, and read the manual and or get advice first. If needed, see Rule number 2, the law of situational discernment. And finally, the law of preventative equipage. Safety equipment exists for a reason. You're the reason. Get it and use it. Yes, we know you're invincible, but use it anyway. It sets an example to those more fragile than yourself. So we're going to start in the actual material of the book. We're talking about voltage and current, and specifically, I like to call it that voltage burns and current kills. So on your left, you'll see the effects of electric current in the human body. It's a table from your book. What I want to point out is in the 6 to 25 milliamperes for women or the 9 to 30 milliamperes for men, painful shock, loss of muscular control, the freezing current or can't let go range occurs. That means that at that point in time, when you have that much amperage going through, let's say your hand will suddenly close, let's say around the tool, the wire, whatever you're holding that's energized, and it will now not let go. And oftentimes this will also cause involuntary jerking of your legs or other arm. And if you're on a ladder, that means you're going to be dropping right off the ladder at the same time, which may break the circuit, but also the ground will break your fall. But I want you to notice that 6 to 25 milliamps or 9 to 30 milliamps, that's not very much current. It doesn't take a lot of current to cause an injury to occur. When you get to 50 to 150 milliamps, extreme pain, respiratory arrest, severe muscular contractions, and death is possible. So let's think about that. 50 to 150 milliamps. That is 0.15 amps. It's not even amp. It's 0.15 amps would be the top of that range. Not a lot. And when you get down to 1,4300 milliamperes, which is 1 to 4.3 amps, rhythmic pumping action of the heart ceases, you're in cardiac arrest, muscular contraction and nerve damage occur, and death, well, likely, is most likely. Now, I want you to look at the other side, the picture here, and we see that we have a number of things that can happen when we have severe electrical injury. First, you get an entry burn somewhere, and if it's going across the body, like in this illustration, from one hand to the other, you're going to get an exit burn, which means the path of the electricity traveled across, up the right arm, across the chest, and then out to a grounding point on the left arm. And of course, this can cause all sorts of interest, or not interesting, but also terrible situations. However, what I want to put forward here, because you may end up at some time in the future seeing somebody who may have been electrocuted in real life on the scene, and you may be the first person around them, is that they're not only electrocuted, they also probably have fallen, and they may have fractured bones or head or back injuries as well. Notice the wire across that person's body. First question before you do anything is to assess from a distance that, hold it, why is that person on the ground? Oh, look, there's a wire. Is that live? Is that wire live? If it's live, we've got to turn it off first before we can actually deal with that person, mainly because there's a good chance that that wire will kill us or injure us badly if we go to help this person and try to remove it without any special equipment or any get in proximity of it. So be very aware of that when you're dealing with somebody who may have suffered an electrical injury and they're unconscious on the ground. Where is, or even if they're not unconscious, where is the wire? Where is the thing that caused the initial injury? So what are the precautions to take? Well, when working on equipment, remove any jewelry. And it's preferred that devices are not energized. However, oftentimes if you're troubleshooting, and that means you are trained to troubleshoot, you are qualified to troubleshoot, then you may have to energize equipment to operate it and to test it properly. In that case, you need to take precautions working around energized equipment. For example, you need to use the one-hand rule. So that means that you're basically going to put one hand in your pocket, and you're going to basically work on the equipment with one hand to prevent any way of you having electricity go across your chest. More specifically, if you look at the diagram, ideally you want to use our right hand to operate any of the test equipment and to do anything we need with high voltage, then to use our left, because we do not want this to go across our heart. If we have a situation where we touch a live wire and it has sufficient amperage, and we ground to the floor, to the foot, then we may have a situation, if it's our left arm, that goes across our heart and causes ventricular fibrillation, which is basically means that you're not going to have any effective blood flow. If it's on your right arm, there's less chance it's going to cross your heart if it's coming out of your right leg. And again, you can see hand-to-hand contact, as we used in the example on the previous slide, goes across the chest, across the heart. We can also have hand-to-arm contact, which of course means you're burning your section of your hand, but it's not going across your chest. Or you can have it come actually, in certain situations, depending on what you're working on, especially around high tension wires, if you're a lineman, of course, which is not the case, but you can have it go across your head. Not a great thing to do either. So just be cognizant of using one hand when working on energized equipment. Make sure you don't bypass safety interlocks. Was there an exception to this? Yes. If you're a qualified technician whose job it is to work on this kind of equipment, you may have to disengage the safety locks and work on something that has a safety lock that's been bypassed, because you cannot energize the equipment. For example, if you took the top case off this piece of equipment, the safety interlock might then prevent the equipment from being energized and you cannot troubleshoot it. So those people who are qualified know how to bypass the safety interlock, but they're also being very cognizant of how to work on this material. You are not a qualified electronics technician, so do not work on energized equipment. Make sure capacitors are discharged using a meter or a grounding stick. Ideally, I would go with a grounding stick. And that way you don't have any residual charge in the capacitors that will discharge through your, let's say, your hand when you're trying to move the wire harness in some way. Never accidentally short batteries. That is, don't get any metal that bridges the gap between terminals on the batteries, because then it'll be an uncontrolled rate flow of electrons, which is also called a short circuit, and that will heat up that metal very hot. Not only could it burn you, but if it doesn't melt, it will actually cause the battery to burn as well, potentially explode in some situations. So don't do that. Please avoid that. And of course, don't work alone whenever you have energized equipment, especially on any high voltage. The next thing is to just be familiar with the power cord color codes. We have the direct current on the left side, and this is both of these are for the US. And what we have here is an example of a Yaesu FT991A power cord. We have, basically, I want you to just see and focus on, we have two colors. Black is ground, or the negative terminal of the battery. Red is the positive terminal of the power supply or battery. These items, most power cords for transmitters have their own fuses, and these have a fuse both in the ground side and the positive terminal. And then oftentimes radio like the Yaesu or ICOM have locking power plugs, which means you can put them into the back of the transceiver and then it will lock in place. You'll have to push down on a key or something that will release it. This way it doesn't actually fall out on its own. There are power cords like using Anderson power plugs that are very popular, but they have no resistance to actually being pulled apart. And so that's one of the downfalls of those. They're very convenient, they're easy, a lot of amateur radio operators use them. It's almost a standard in the hobby, but they don't have a locking mechanism to keep them together with the thing they're powering. So if somebody walked by and accidentally, push trip on the wire or lean against in such a way that it could have enough force, it'll just come apart and de-energize. On the right side, we see alternating current in the United States. And first thing, this is a plug. This is what's called a polarized plug, which means we have the two blades, the two vertical blades. One is longer than the other. The one that's longer is the neutral, which is white. The one that's shorter is hot or black, which is usually a black or red wire. So neutral is a white wire. Hot is generally a black or a red wire, usually black. And if you're ever hooking up a switch to 120 volts, you want to make sure the black wire is what you're switching, not the white wire, because that's neutral. And green is the safety ground or earth ground going to a ground rod outside the house or the building, and that is generally green. Sometimes you'll see it green with a little bit of a yellow stripe to it. So on safety grounding, obviously use the three-prong power cords on all AC lines. Number one thing to do. Otherwise, if you don't and you need that safety ground, you're not going to have it. There is a practice that some people did in years ago where they would cut the third prong, the earth ground, off because a lot of plugs didn't have the third one in, and so they would cut them off, which was not a good practice. There was a way of dealing with that, but they were taking an easy route and they cut it off. But please don't do that, and modern outlets today all have the ability to take a three-prong plug. Safety grounding on the left side, I want to just make sure that current carrying capacity of some common wire sizes, this is from your book. As I've said in a previous session, you want to make sure the wire is sized to handle more than the current that you're going to put through it. Remember, a fuse is just a wire. And it's a small enough wire that if it gets a certain amount of amperage, it creates so much heat it burns up and breaks the circuit and causes like a switch to open. And this can happen if you're taking, let's say, the 6-gauge wire. It has a allowable, excuse me, not the 6-gauge, 14-gauge wire, the one at the bottom, and its allowable current is about 20 amps. And we have a maximum fuse or circuit breaker of 15 amps. That gives you a safety margin, so we actually fuse it at lower capability the wire is able to. But what would happen if I tried to draw 30 without a fuse? If I didn't have a fuse, I just had wire going to whatever the device was. If I try to pull 40 amps out of a 14-gauge wire, well, it would heat up so much that it may basically melt and open the circuit, or worse, wherever it's running, it gets hot enough that it could cause a fire from the materials around it. So it's very important to use the right size wire for what you're doing. So if you need 20 amps, go with something like a 12-gauge, a wire that'll carry at least 25 amps. So you want to always make sure that you are using a wire that gives you a safety margin for the amount of amps you're carrying, but you're fusing below the maximum capability of the wire. Again, another form of protection. Make sure all devices in the shack have a connection to safety ground. It's very important. Use a ground fault circuit interrupter or circuit breakers on AC lines. Use fuses on DC lines. Again, what we want to do is make sure that if there's going to be a short circuit, we want to protect the wiring of the house or the wiring of the battery from also experiencing that same short circuit. So that's what these things are designed to do, is they're deciding when the current is going up high enough, the GFCI breaker will then open up like a switch and stop the flow of electricity. Our fuses, as we discussed before, will melt and open up the circuit. Use an AC outlet tester to ensure the hot is on the correct prong. So a lot of people don't do this, but if you really want to be, make it right, because some things need to have the hot side on the hot side. So there is special devices. They're not very expensive. They're probably less than, around $10 or $12. And they tell you if you put them into a receptacle that's powered, it'll tell you that if that receptacle is wired correctly, where the hot is on the correct side of the receptacle and the neutral's on the correct side of the receptacle. Why? Think about this. If I said before, the AC hotline, if there's going to be a switch in the circuit, the AC hotline is going to be sent to the switch. If the outlet was miswired, that means the neutral side was on the switch, which means when you turn off that device, when you think you're turning off that device, you still have the hot side of the plug, the hot side of the power line, basically on the wires in the unit. So if you were reached in thinking that was off, it's a good chance you're going to get shocked. So that's why we want to make sure everything is the way it is to code. And of course, don't overload AC outlets or exceed battery capacity, and never replace a fuse or circuit breaker with one larger than the one being replaced. And all towers, masts, and antennas. That is, all towers, masts, and antennas. And this is specifically metal ones because there can be fiberglass or carbon fiber masts. But any metal towers, masts, and antennas should be grounded per local safety codes. Now, RF grounding, you don't want to get bitten by RF. And then we call it, you'll hear that term every so often in ham radio, the RF bit me. Well, it can happen if you're, depending on the situation. If you have a lot of RF coming back in your shack, it's possible that, let's say you pick up an old style metal microphone and you key the push to talk, it could possibly give you a little shock. And so that's what's called being bitten by RF. So equipment in the shack is tied to a common grounding block and then to an earth ground. So you see the picture below, and we have some flat silver braid, and all those mostly in some single wires. They all go to grounding lugs that are on your equipment, going to a common ground point, and we keep those wires as short as possible. And then from there it goes to the grounding rod outside the house. And again, ground rods, we might have at a house multiple ground rods. There's at least 2 in modern construction. And then you might be adding a ground rod for your tower, or a ground rod for your radios that's separate. All ground rods should be bound together with heavy wire. Bounded means that we're going to run a wire from across each ground rod so that every one of them is connected wherever they are around the house or around the tower, so that there's basically no breaks in that ground. That's also a great way if you have an SWR problem or audio problem, sometimes that can clear that up. But every ground rod should be tied or bound together. And oftentimes in a house you should see that those are all grounded together if you have multiple ground rods at a house. And then using lightning arresters on antennas. And a lightning arrestor is a special device, and it has a gas-filled cartridge that, think of it like a fluorescent light, where if there's so much electricity from a lightning strike coming down the coax line, from the antenna down the coax line, then what's going to happen is that gas gets ionized and it creates a path to the ground lug, which goes to your grounding rod. And the purpose of that is to shunt the lightning from your coax line that's going to into your house to the grounding rod on the ground. And the purpose of that is to protect your radio and to protect your house. Now, the ideal situation, of course, is not only to have a lightning arrestor, but to have a switch disconnect inside the house, so that if you're seeing a lightning storm coming, you want to make sure that you just turn the switch on the antenna so the switch is disconnecting your radio from that coax line, and then when the thunderstorm's over, worry about thunderstorms over, you can switch it back to your radio. But lightning arresters are an important thing for fixed locations and for protecting your radio. Yes, your antenna is going to be fried, your coax is going to be fried, but the ideal thing is your $1,000 radio is not going to be fried. And then use RF chokes on coax cables before the antenna. We'll get in a little bit more on the chokes a little bit later. But RF chokes on coax cables are used to reduce the return RF coming down the braid of the coax to the radio. and this will cause issues with some radios. Either A, the power level will be coming down and may be very small, so it's going to be absorbed by the coax, absorbed by the radio. It's not going to have any problem, but it's very high. In most modern radios, they're designed, if that happens, to begin cutting back the power on the transmitter to protect the final amplifier. So if you have a high RF, it's going to basically cut back the output of the transceiver as it protects itself. So we use RF chokes to choke off that RF current back down the coax cables to prevent it from going into the Radio Shack. So RF interference is a big topic. In some respects, it used to be a big topic for amateur operators and their neighbors and how they affected them. Today, it's actually the reverse. It's more how your neighbors are affecting you. But let's talk about that. One of the things is that there's perceptual issues. Once people find out you operate a transmitter, be ready for them to blame any issue on you. My cable TV went out. What did you do? There's snow on my TV. It must be you. My coffee maker turned on by itself at the wrong time. It must be you. And then, bottom line is most likely it's not you. In fact, most likely you didn't even have the transmitter on or the transceiver on. But on the same token, yes, you could interfere with some domestic equipment, and you're obligated to correct that situation. So, for example, I ran into some air cleaners, domestic air cleaners, very cheap capacitive switches, and it turned out that those switches were not really built to handle a good quality capacitive switches. They're built to be basically opaque to radio frequencies. So what's happening is that plate of those capacitors and the capacitive switches were picking up RF energy, and therefore those air cleaners were turning themselves on without anyone touching them. And the problem with that is that you can easily get rid of power line RF through RF chokes, but that situation was a manufacturing defect for all intents and purposes, and the amateur radio operator cannot fix that. But it is irritating for people who want to use that kind of equipment, so that can happen. So if you do interfere with domestic equipment and it's legitimate, they can show, or you can show that it is you have some obligation to correct that situation. Of course, it's not the other way around. If they're using LED light bulbs that don't meet proper specifications, they use a lot of wall-based power transformers. These all put out a lot of RF if they're not designed correctly. They interfere with your radio. Solar charges, if they have them, will interfere with your radio, but they're not obligated to correct those. Now, there's an exception to this, and that is if the power company has a problem with the power lines around you that's causing RF to interfere with your operation, they are obligated to fix it for you, but you're going to have to go find it before they fix it. So to eliminate any stray RF on the transmission line is the first starting point for any way of fixing these kind of problems. And there's two methods, filtering and choking. And I mentioned a little bit about choking, but I didn't define it. Filters, like low-pass ones, remove or suppress unwanted RF. So there are filters that are designed to actually take out certain frequencies out of the line so they cannot interfere with you or you interfere with somebody else. So you might have to put a low-pass filter into somebody's device, or you may have to put a low-pass filter in your device so that you can then handle the situation that's interfering with you or interfering with them. Now, the reason it's not so much a problem today with you interfering with them is because in analog TV, the channel 6 used to be about right near the amateur radio band for 6 meters. So it was not unusual for people transmitting near somebody watching channel 6 that channel 6 would see something happen to their TV sets on analog in the analog world. And so this was not uncommon, and this had to be fixed. But in modern day with digital TV, we don't see that problem. Now, RF chokes are ferrite materials. That means they have some iron in them and other materials, and they eliminate RF from cables. And for example, if you look at the picture on the right, we see the little guys in blue and the little guys in yellow. The yellow represents the noise. And when a wire is put through this ferrite material, the noise, that ferrite acts as a resistance to that noise, and therefore it filters it out and prevents it from going down the line. And you can see on the blue picture how we basically wrap that wire around twice, so it goes through the toroid at least, or through the ferrite at least twice. And so this is a form of suppression of RF because the toroid is absorbing that RF and it's blocking, or it's blocking the signal, the noise that we don't want, and it's allowing to pass the signal we do want. And of course, always use shielded cables when you're passing RF because this helps reduce any stray or leaky RF. So it's possible like your cable TV can leak, cable TV transmission lines could be bad or broken cables, and that would leak RF that might interfere with you. Now, let's talk about putting up and taking down towers. To state the obvious, it's dangerous. So it's really important. Leave this work to fully equipped and trained people. And purchasing a climbing harness doesn't make a person a tower monkey. So this is really important. If you have not invested in the right equipment and training to work with a tower, you should stay off towers. They are dangerous. And we're talking, the one in this picture here is about 40 feet from top to bottom. And they can be as high in amateur rate up to 200 feet in some cases. And even higher in different locations if you get the approvals. And what you're not seeing is this is the assembly of the tower. They haven't put the antenna on yet. And the antenna that's going to go up there is probably about 30 feet by 20 feet, or excuse me, 30 feet by 30 feet in dimensions. It's a 3-element 20-meter Yagi antenna, so it's very big. And it takes about, when we're putting it up, from taking it from the ground up into the air, it takes about 6 or 7 people to lift it up into position so that it can be lifted up into the air. And then it takes 1 or 2 people who have to really be trained to move that antenna into position around the guy wires to get it located at the top. And what they're wiring at the top right now over there is the rotator, because that antenna is designed to rotate. And so again, if you're not trained to do this work, don't go up a tower. No matter what the situation is, no matter if you think it's only going up 2 or 3 rungs to do something, stay off the tower unless you're trained to do it. So the other thing about towers and masts, or some things to remember, is place antennas and supports well clear power lines, including feeders to the house. It's not unusual, and this has happened every so often, every 10 years or so this happens. People are putting up a tower or putting up a metal mast. They're not paying attention to where the power line is. Suddenly they're grabbing onto it to lift it, and it starts to fall. And they're holding onto it, trying to prevent it from falling. It hits the power line, and they are all electrocuted. This has happened before. So please separate by 150% of the tower antenna height away from power lines. Plus make sure you have at least 10-foot clearance of an area where there's a fall. So if you think about, okay, this antenna is going to fall, it's going to fall like this, then make sure you have at least 10 feet additional clearance around the fall area. Also, never attach an antenna to a utility pole, and towers need to be grounded with an 8-foot grounding rod, as we mentioned before, and use a safety wire on guy line turnbuckle. So here you see on the right a turnbuckle in the top, and on the lower picture we see the turnbuckle is there putting tension on the guy wire, and then we put another wire around the turnbuckle that prevents the turnbuckle from unscrewing itself over time from thermal issues, from summer to winter. It can slowly begin to contract and expand, which starts rotating and loosening it. So to prevent that kind of situation, we use a safety wire to lock it in place. And always, as I've mentioned before, have a ground crew. Don't try this at home by yourself or in the field by yourself. And of course, hard hats, eye protection, and gloves are important when working around towers and masts. Trust me, whatever goes up is going to come down and most likely land on your head. And that includes the person up on the tower who's not trained to how to lock themselves in with the harness. So recently, probably about a year ago, what came into effect was every amateur radio station is supposed to do RF exposure limits. It is the law. You're supposed to be able to at least have done the calculation and have it available so you can then make people who live in your house or around you aware if there's an issue regarding that. So the first thing to remember, as we've talked about before, radio frequency is non-ionizing. So just like your microwave oven, which is 2.45 gigahertz, it is a radio frequency. that frequency is high enough, let's say 1500 watts. It's bouncing around the microwave oven, is interacting with the water molecules, causing them to vibrate, and vibration means heat. So RF of sufficient frequency and energy will cause water and other molecules to vibrate or heat. And RF, as I said before, is non-ionizing. It can't cause an electron to leave an atom or molecule. So to do that, remember, we have a place where we talk about ionization. That's in the ionosphere. And that is taking enough solar energy is coming from the sun, hitting atoms and molecules, and able to energize them enough to knock an electron out of the orbit of that atom or molecule. Radioactivity does the same thing. Those are ionizing radiations. RF is non-ionizing. It only produces heat. So does this mean that RF is harmless? No. Just as a candle isn't harmless, RF isn't harmless. Yes, it is possible to be burned by a candle. It's possible to be burned by RF. So RF can cause, as I've said before, heating of the body tissues given the frequency, energy level, and distance from the source. The body can absorb more energy at certain frequencies than others, and the total amount of heat is related to the RF field intensity and frequency. And we usually measure this in what's called specific absorption rate. So the body is resonant at 35 megahertz if it's grounded, up to about 70 megahertz if it's not. Individual body parts resonate at higher frequencies. They're smaller portions, so they're like smaller antennas. And for example, the head can resonate at 400 megahertz. So frequency is of the highest specific absorption rate, span 30 megahertz to 1500 megahertz. So this is the RF exposure calculator provided by the ARRL, the Amateur Radio Relay League. And here's the URL for that. So you can make the calculation for yourself. And the FDCC mandates testing and evaluation to ensure exposure levels do not exceed the MPE or the maximum exposure limits. Licensed amateurs are responsible for ensuring no one is exposed above MRE. Actually, MPE. I got to fix that. So we have two areas that we're concerned about. One is controlled environment. And in controlled environment are people who are aware that you're operating. So for example, if you're operating in your house, this would cover everybody who lives in your house. That is in the controlled environment, which means because they're aware, they're more able to take precautions about situations, and are therefore, and also will be exposed to the field probably more regularly. The second was in the uncontrolled environment. They're not aware of your operation. They're basically transiently moving through your environment, or maybe they live next door in some way. And so therefore they are not in the controlled space. They're not in the immediate vicinity of your operation. And then we also take in consideration the duty cycle of transmission. So different modes have different duty cycles. FM is 100% duty cycle versus other duty cycles like SSB are without speech compression or speech processing is about 20% of a duty cycle. With conversational SSB heavy speech compression, it's up to 50%. And then we think about how many minutes are you transmitting at a time versus how many minutes you're receiving. So let's assume that most of the time you're in conversation, which means you're probably transmitting for 30 seconds to a minute, then somebody else is transmitting for 30 seconds to a minute, and you're having a back and forth set of conversations. So that would be probably the worst case. In many cases, like in contests, you're transmitting for maybe 15 seconds out of anywhere from 1 minute to 5 or 10 minutes. Antenna gain is each antenna has some level of gain. That is, remember we talked about antennas. It's kind of like putting a reflector behind a light, like in a flashlight, which focuses the beam and makes it appear to be more intense. So in the antenna gain in this case, let's say is 2 dBi, or decibels with respect to the isotropic antenna. And we have the operating frequency here at 14.2 megahertz. So this is the form that we would use on the ARRL website to make the calculation. So let's assume we're operating at 146 megahertz at 50 watts FM with a gain of 3 dBi. That calculation means that we cannot have anyone closer than 3.3 feet from the antenna in a controlled environment, and we can't have people more than 7.4 feet to the antenna in an uncontrolled environment. So let's look at another example. Let's take 14.2 megahertz, 100 watts SSB with compression. We have 1 dB of gain. We have a controlled space of 1.2 feet, an uncontrolled space of 2.8 feet. So anybody who's in an uncontrolled, that is, they're not part of the household, let's say, or not part of the people who are operating. Let's say we have a group of people operating together in a contest in a field location. If anybody who's walking through that area would have to be no closer than 2.8 feet from the antenna. So let's do some more calculation examples. At 146 megahertz, again, that's the 2-meter band, at 100 watts single sideband. Remember, we can do weak signal work, otherwise known in this case as single sideband, or it could be CW, at 100 watts. And we're using a Yagi antenna with 15 elements, so we have a gain of about 17 dBi, 17 decibels with respect to an isotropic antenna, which means because it's a very tight focused beam of energy, the controlled space is 11.7 feet and the uncontrolled is 26.2 feet. So you can see that we're at a high frequency, we're at a much higher power, and we have an effective gain that's very, very high. So therefore, we have to have a maximum permissible exposure. We have to have a controlled and uncontrolled space that's much further, much wider than we had before. 146 megahertz, 50 watts using FM. Remember, FM is 100% duty cycle. With that same 15 element antenna, we now have a controlled space of 16.5 feet and uncontrolled at 37 feet. Why? Because remember, SSB has a lower duty cycle than FM has, because FM is 100% duty cycle, and SSB is going to be 20 to 50% duty cycle, depending on if you're using compression or not. And because of that, we have different controlled and uncontrolled spaces given the same antenna, and even less power. So let's look at UHF, 446 megahertz, 50 watts FM, again 100% duty cycle with sound compression. Well, we're going to have a 17 dB antenna again, and we have a controlled space of 13.5 feet and uncontrolled of 30.4 feet. Why is this so? Why is it less? It's less because, as we remember, different frequencies have different absorption rates with the body, so therefore the calculations take that into effect, and at that frequency we actually have less space that we need to keep people clear from. And so this is a calculation you do whenever you're setting up an antenna at your home location. Your mobile and portable stations are exempt from this. However, it's highly encouraged you're cognizant of this for your mobile and field operations, and therefore you make sure people are safely and distant from your transmitting antenna. If it's a car, you want to put the antenna as far as you can away from the passenger compartment. Again, you need to take in consideration that for most cars and mobile and HTs, we're operating at very low powers, and therefore we don't have as big as distance as you have with these, big Yagi antennas. So, closing thoughts. Well, we're done. The closing thoughts. So congratulations, you got through this course. And I just have a couple of closing thoughts for you. One, set a date to take the test, because if you don't set a date to take the test, if you don't set that goal with the actual date, chances are you're going to keep putting the test off and maybe you'll never take it. As always, prepare and practice. Read the book, do the practice questions over and over again, and take practice tests over and over again. When you start to see yourself getting consistently 80% or higher, that's a good time to start going for your test. And of course, be successful and pass. Just remember, the test is no different than the practice test. You've taken a lot of practice tests, you've gotten consistent 80%. Know that when you go in to take the real test, you are going to pass because you've already taken it numerous times. Then pay the FCC and get your call sign, and then get on the air. So hopefully, somewhere in the future, I'll hear your call sign on the air, and we'll be able to make contact. Thank you very much for taking the class. I appreciate you putting the time in, and I wish you all the best.